All right, so the last two videos talked about, in general, how resistance, membrane resistance, and capacitance will influence the response of a cell to an injection of current. What we're going to do in this video and in the next video is talk about is to really get quantitative about that. So we will be introducing equations that will be able to tell you exactly what the voltage should be after an injection of a certain amplitude of current, with the cell having certain properties. And so that will allow us to solve equations and think about problems that require like precise answers. So let's go ahead and dive in. So in this video, we are going to address time, how voltage changes over time if you give a certain current. And the next video will be about distance. But kind of just to give an overview of all of that. As we've been talking about, right, you can treat the membrane as a resistor and a capacitor in parallel. And the capacitance comes from the ability of the membrane to store charge, and the resistance comes from the fact that ions can't just go through the lipid membrane. They need to find a channel to do so. So, how can we precisely calculate how the membrane potential will change in both in time, like after you apply it, if you wait a certain amount of time, and also in space, if you inject it in a certain location, what would the voltage be like over here, a certain distance away, after delivering a certain current? And these questions matter. It matters for the speed of starting an action potential. So I open up some ion channels. How fast is the neuron going to be able to respond? And also how it will spread throughout a neuron, especially up and down a dendrite or an axon, to cause things to happen in other parts of the cell. So this is the full equation. Don't worry, this is the only time you will even see calculus in this course, and you will not be expected to do calculus because this differential equation is very, very unwieldy, even for people who kind of like do this kind of math for a living. And what we're going to be doing here is going to be kind of a simplification of this equation. Um, but it's good enough, and in a lot of cases, it will give you some idea of how real neurons actually work. And so this one, right, it's in two parts, and we can split them apart and kind of deal with the distance aspect versus the time aspect separately. And so what we can do, this latter half is about time because we got that T there. Basically, we can pretend the neuron is a sphere and ask, when I inject a current, how does the voltage change over time? This first part here is about distance. That's what the X is, like the distance, like an X-axis, the distance away. So we can model the neuron as a cable. And honestly, like dendrites and axons are like cables, right? Like long tubes. And then you can ask, when I inject a current, how does the voltage change over that distance? That is going to be the next video. This video is going to be about over time. So before we do anything mathy, and before I show you any equations, it's important to sit back and really understand, like qualitatively, what is going to happen. Um, what I've found is that when people jump to the equation first without an understanding of like what is going on in the cell and in the biology, it gets really, really tricky. You don't know what to put where, and you don't know how to verify that your answer makes sense. And sometimes you don't even know how to get started because you don't know what's going on. So what we're going to do here is just kind of talk about what is going on inside the cell and what is happening with the voltage, just like in general, without any numbers, um, when you inject current and when you stop injecting current. So before we do anything, right, the neuron is at rest, it's at rest. Okay. And then we're going to start, and right, rest is given by the GHK equation, as we've discussed earlier. So that's all about that. That's it about that. So we're going to start injecting current. You can literally do this with an electrode, or you can, the cell might open up some ion channels and current is flowing in that way. Okay, so we're going to inject a positive current. So positive ions are coming into the cell, and it's going to make the cell more positive. Okay, so the voltage will go up. It will go more and more positive. And it does this slowly. Why? Because there's capacitance there, siphoning off some of the effect of the charge. Um, um, right, we'll be able to calculate exactly how fast or slowly it goes up with the equation, but it will just generally go up, right? But it won't go up forever. It will go up until you reach the maximum voltage given from V equals IR. So even if you inject for like minutes and minutes and minutes, which is an eternity for a cell, you will never get above that V from V equals IR. And by the way, that V from V equals IR is not like an absolute value. It's not going to be like, oh, rest was negative 65 millivolts and this V is going to be negative 30 millivolts. No, that V is always the change from rest, the absolute change, or sorry, the distance from rest, not the absolute or the raw value of the membrane potential. Okay. So when you inject current, it's going to go up and up and up and up until you reach that V from V equals IR. And it's going to hang out there as long as you're injecting the current, it's going to hang out there at that max value V equals IR. Okay, what if you stop injecting the current? If you stop injecting the current, the voltage is going to go down. And it's going to go down gradually, but it's going to go down, 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 down. Not forever. It's going to go down, 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 down until you go back to rest. So qualitatively, that is what's going to happen. So keep that in mind as we put equations on it so that you can put numbers on it. Okay, so right when you inject positive current, the voltage rises. When that happens, you want to use what's called the ascent equation because the voltage is going up, right? And ascent means like ascending means going up. So here is the equation. Just a moment. I am going to fix something. Okay, there we go. So this is the ascent equation VT equals V infinity times 1 minus E, like the number E, to the negative T over tau. So VT is the voltage at time T above rest. So this line here kind of shows V10, right? So V10 Y10 because this is 10 milliseconds after you started injecting the current. So 0 times 0 is the time you started injecting the current. And so this is the 10 milliseconds in this case later afterwards. And this is the V. This is not the raw V. So like if rest is negative 65 and this is negative 32, the VT is not negative 32. It's the difference between negative 65 and negative 32, which is 27, yeah, 27 millivolts or so. Hope I did that math right. Okay. So, similarly, Vmax is the eventual voltage, but it's the amount above rest. And so if this value is negative 35 and this value rest was negative 65, then V infinity is 30. Okay? Because that's how much it is above rest. By the way, this is also the V that you get from V equals IR. That V is also a change from rest, so you can plop that right in if you need to do that calculation. So the final thing we don't know, or we want to discuss, is tau. What is tau? So tau is the time constant, and that tells you how quickly or how slowly the voltage goes up. And it has capacitance in there because the capacitance is a major determinant, right? Because it's the capacitance that is preventing it just from the voltage from jumping up right away by siphoning off those charges. So to calculate it, you need both R and C, but they need to be like the same. So if you have an input resistance but a specific membrane capacitance, you got to change either the R or the C in order to match the other. So you could have both be the input, like input resistance times input capacitance, or both be the specific per area, so specific membrane resistance or specific capacitance, or both be per length, but they got to match. Okay. Also, if you don't know R or C, but you do have a graph of what the neuron is doing, you can estimate tau. Tau is going to be roughly the time it takes for the voltage to reach 60% of its final value. And so that's what's outlined here in this particular case. All right, so that's when you inject current. There are some tips and tricks for using the ascent equation. Um, a lot of this is about units, so VT and V infinity are going to match in units. So if one's in volts, you gotta, and the other's in millivolts, you gotta change one or the other. It doesn't matter which one you change, but they gotta match. Okay. And also conversely, that means that if you're calculating VT and the V infinity is in millivolts, you will also naturally get the VT out in millivolts. Time and tau also need to match in units. It's very popular for the time to be in milliseconds. But the problem is here is that if you multiply R and C together, that will usually give you seconds. And so again, it doesn't matter which one you convert, but they have to match. So big picture, stepping back, in general, when you're doing the unit conversions, different if your equation involves multiplying or dividing different kind of types of units together, you have to convert them to the base unit. So for example, to calculate tau, you're multiplying a resistance by a capacitance. Those are different types of units. And so you need to put them back in the base units. You need the R to have some form of ohm in it, not mega ohm or anything, ohm in it. And you need C to have farads, not microfarads or picofarads, but farads. Okay, so you need to do that conversion before you can multiply them together to get tau. However, if you're dealing with things where it's like it's the same type of unit, but it's just like they're both time, right? The time constant and time are both time, but they might be like different types of time. Then it doesn't matter which one you pick, they just need to match. And so if one's in seconds, the other is in milliseconds, you can change tau to milliseconds or you can change your time to seconds. It doesn't matter. Just do what's easiest. They just need to match. Okay, so that's about the unit part of it. Um, so both, and again, I want to reiterate because this is something that a lot of people find difficult and need to hear again and again. Both VT and V infinity represent changes in voltage, not the absolute voltage. So often you'll get values, right? That is like, oh, it rest is -65 and then it went up to +10. Those are not the values that you plug in. You have to find the distance between them. Okay. And so V infinity is the eventual voltage minus the baseline voltage, so the voltage at rest. That's also the V from V equals IR. Right? Because the V from V equals IR is also the change in voltage from rest. And then VT is the voltage at time t minus the baseline or rest voltage. Okay, so it's always a difference. So that's I always like to sketch things out. And so I can see like what is an absolute thing, like -65 millivolts, and what is a difference between that baseline and the value. Okay. So what about going down? When you stop injecting positive current, what happens? Well, the voltage will fall. And so you use a different equation for this called the descent equation. And descent is about falling, so that's why it's called that. Now, one thing here that I want to point out is that you got to be careful with the time here. So the time is 0 here. It starts when you take away the voltage and when the voltage starts falling. Okay. So for the ascent equation, you started the t equals 0 was when you started applying the current and it started rising. Here it's when you take away the current and the voltage starts falling. Okay. I just say this is a little bit tricky because sometimes there will be questions about like, hey, you applied the current for 5 milliseconds and then you took it away and it started falling and it'll ask about what happens like, okay, a millisecond after it started falling. You might be like, oh, well, I should start the timer for t equals 0 at the point where I applied the current, right? Because it says I applied the current for 5 seconds. No. If you're using the descent equation, you should always put the zero, the t equals 0, as the time when it starts falling when you take away the current. Regardless of how long the current was on for, the t equals 0 is when you take away the current. Okay, so the equation here is VT equals Vmax times e to the negative t divided by tau. So again, VT is the voltage at time t above rest. So this again is a delta, so or a change in voltage. So it's going to be the change in voltage at 10 milliseconds, for example, for V10 over baseline, which is over rest. Vmax is the starting voltage, right? Because it's never going to be bigger than that, right? Because it's falling. So Vmax is the starting voltage above rest. And then tau is the time constant. This is the same time constant as before. A neuron is going to have the same tau for the ascent and the descent equations, and you calculate them the same. So again, tips and tricks here, very, very similar. Vmax and VT have to match in units, usually millivolts, but really they just have to match. T and tau must match in units. So you usually it makes sense to think about neurons activities in milliseconds, so usually that's what you want to convert to. And then again, both VT and Vmax represent changes in voltage, not the absolute voltage. Okay, so how does this work in practice? Well, let's try this question. So you are recording from a neuron whose resting membrane potential is negative 65. You stimulate a small patch of dendrite at the tip of the neuron of the tip of the dendrite with a current of 500 picoamps. After a while, you measure the voltage in that spot to be negative 15 millivolts. So after a while, that's going to be key. You know the input capacitance, it's 50 picofarads. So if the neuron were at rest, how long would that 50 picowatt current need to be applied to make the neuron reach threshold at negative 50 millivolts? Go ahead and think about that for a bit. Okay, so what's your first step? Your first step should not be to pull out an equation or something like that. Your first step should always be to sketch the situation first. If you sketch the situation first, that will make sure that you understand what's going on, right? Because if you try to sketch it and you don't know what's going on, then you know that you have to ask a question or reread the question or something like that, right? So sketch the situation first. A lot of these things are going to be much easier to see with a sketch than just like in your head. And especially it's really easy to get tripped up with things like the absolute membrane potential versus the like change in membrane potential, which is what all the V's are. So we want to be sure what's going on here. Okay, so let's do that. We're injecting a current. So this is the current. So at first it was like 0, and now it's increasing to 500 picoamps. That is also going to be our T0. So how is the neuron going to respond? Well, the membrane potential was at negative 65, right? And it is, once you start injecting the current, it's going to go up and up and up. And it says you measure it. So after a while, right? So we're going to assume like a long time, it's going to be negative 15 millivolts. Okay. So that's what it is. That's what the baseline situation is. What about the question? So it says, how long would it need to be applied? So we're looking for some sort of T, right? That's what we're looking for to make the neuron reach threshold at negative 50 millivolts. Don't worry about the word threshold. Just pretend that isn't there. Let's just think about how long would it need to be applied for the voltage to be negative 50? Where's negative 50? So if that's 0, negative 50 is like there-ish, right? And so that's kind of our target there. So we're wondering how long will it take if you apply it here for the voltage to go from -65 to -50. Okay. Now we have our sketch. We'll be using that to figure out everything about the situation. So at this point, what's the pertinent equation? Which one should we pick, the ascent or the descent? What do you think? Okay, we should choose the ascent. That is appropriate here because we are applying a current and the current is going up and it's asking how long it takes to rise to a value. Okay, so let's start plugging things in. So VT, do we have VT? So actually we do have VT, right? Because we want to find T. Right, but we have the VT. Is it -50? Right? Because the question is asked, how long would the current need to be applied to make the neuron reach -50? Is that our VT? What do you think? Okay, no, that is not actually the VT. Because remember, the VT is not like the absolute voltage, it is the change in voltage from baseline. So it's not being like, oh, -50, you put that in. What you need to figure out, how much is -50 above the baseline of -65? And the answer to that is 15. Okay, so VT is not -50, it is 15 because all these V's in these equations are the change from baseline, not like the absolute membrane potential. Okay, so we have our VT being 15. Now, moving on to the right, we have V infinity, and that's the voltage after a long time. And a long time, after a while, all that means just a long time. Okay, and it says the voltage after a long time is -15 millivolts. Is that V infinity? No, so same logic. V infinity is the change in voltage from baseline. And so it's the difference in voltage from -15 to the original -65. So that would be 50 millivolts is V infinity, not -15. Okay, keeping going, T, that's what we're looking for. Okay, tau. We need to get tau. We already have the input capacitance, so let's go with that. So let's go with the equation for tau that uses input capacitance. And so that would be input capacitance times input resistance. What's the input resistance? Ooh, so for this one, we need to use an old equation, right? Um, so if you recall, the R in V equals IR is the input resistance. So what do we have? We do have the V, right? The V is the same as the V infinity. That's our 50. That was our change in voltage from baseline. And we have the I because that's given in the question. And so we can use those things to calculate the input resistance. So rearranging V equals IR, we have R equals V over I. V is going to be in the 50 millivolts. But remember, when we do V equals IR, we're multiplying and dividing things that are in like different types of units. And so we have to change everything to the base unit. So in this case, that's volts. So we're going to change that 50 millivolts to be in volts. Okay, the I, same thing. We're going to change that 500 picoamps to be amps. And then we're going to do that division and we're going to get this number. It's 100 mega ohms, but we can keep it in ohms for now. Why would we want to keep it in ohms? That's a really unwieldy number. Well, I'll let you think about that. What's tau? Okay, so the time constant, going back to what equation we're using, is going to be the input resistance times the input capacitance. And so we can put in the input resistance and the input capacitance, plug it in. Ah, but wait, because we're multiplying things together that are like fundamentally different kinds of units, we need to convert to the base unit. And so for here, we're going to convert that to ohms, which is like what you just calculated back here. And then we're going to convert that picofarads to farads, and that gets you 0.005 seconds. Um, you can keep it that way, or you can convert it to milliseconds if you want your answer out in milliseconds. So again, for V equals IR, we have to use the base units. Same for tau equals RC, we have to use like farads and ohms. Any other of the units, so sometimes you'll have like centimeters in there for the different forms of resistance and capacitance. Those have to like match. So if one says centimeters, the other has to say centimeters as well. Okay, so putting it together, what's the answer to the question? What do you think? All right, so here it all is. Here's the equation. We're going to plug everything in that we just calculated. Then we're going to do some math, move stuff around, do some division. Um, we're going to do some logs here, and we're going to get t is 1.8 milliseconds. And so that is how long this current would need to be applied to make the neuron reach threshold. Okay, I hope that was informative and that going through that example helped you understand how to solve this type of problem. Good luck.